Good day, stat students. So today we're going to talk about section 3.3. We're going to get into more specifics with regards to this type of analysis where we're looking at the association between two quantitative variables. So remember our example with regards to average January temperature and latitude. We're gonna go back to that, and we're gonna get into more details with regards to this example. All right. So first thing is that here's our data, okay, and here's our trend line. And the first thing that you should notice here is that I gave it a name now instead of just generically calling it a trend line. We're going to call it the sample regression line. And actually, if you get into higher stats courses, you'll hear that it's called even something even more sophisticated than this. But for this class, this is good enough. And we're going to call it the sample regression line. Now, why is it a sample? Well, did we take a look at the entire population? No, we only took a look at 10 cities in the United States. And so, thus a sample. 2, we got our line, okay, and then 3, notice I called it the regression, okay, the sample regression line. The reason why is because this is regression analysis. Once you start creating this line right here, okay, and you start coming up with the equation for it, we're doing regression analysis. And so we're going to, from now on, call this the sample regression line or the sample regression equation, okay? So we're going to focus a lot on the line today, okay, and what we can do with it, and for that matter, interpreting it. All right. So back in algebra, you have seen things like this: y is equal to mx plus b. I'm sure that has been burnt into your brain, all right? And so m is what? The slope. All right. Now, here, what I ask you to do is let's not get tied to this symbol right here. I mean, why did we call slope m? Okay. So I don't want you to necessarily get tied to this symbol here. Okay. I'll just kind of warn you of that. But the thing that I do want you to concentrate in on is that slope is always being multiplied by x, no matter where it's located in the equation. Notice here in the equation we got m times x. So you can always identify the slope because it's being multiplied by x. All right. What about b? B is the y-intercept. That's not getting tied down to the symbol b. All right. But y-intercept is what? Sitting by itself. It is not being multiplied by anything. Okay. So you can always identify it like that. So now I got to apologize about something. The reason why I got to apologize is because we're not going to use necessarily this equation right here. Okay, we're going to change it around just a little bit. You're probably going, oh my gosh, why did you have to change it? This is one thing I remembered, so on and so forth. Believe it or not, it's not a big change, but it's a necessary change in statistics, and I'll show you why. So let's say that, okay, so let me show you what the equation is here in statistics. All right, and so we have y is equal to the y-intercept plus the slope times x. And so notice, what did we do? We switched these two things around. We switched the y-intercept and the slope times x around. Excuse me. Why in the world did we do that? There's a reason for it. So let me give you an example. All right, here's the example, and that's let's say that we're trying to predict the value of a house. All right, and so what are all the different things that goes into the value of a house? Well, let's think about it. So you have how big the house is, the age of the house, the condition of the house, the condition of the roof. What else? The house sits on a certain amount of land that you're also buying, so how much land is there? Is it prime real estate? Is it within a big city and you're buying a big lot? Or is it in, say, more, the country, and you're buying a lot of land, but it's not so crowded there, so it's not so expensive? How many bathrooms, how many bedrooms, so on and so forth, right? So all those things can go into the price of a home, okay? And you can model that here in statistics, all right? So here's the thing, is that all those explanatory variables that we just talked about, the size of the lot, the land, the condition of the house, the age of the house, the square footage of the house, all those things that we just mentioned, okay, we can put into the equation. All right, and so notice here on the screen is that this could happen, is that we could have a regression equation where we have y is equal to y-intercept plus the slope times several different factors, and so we don't have just one, we have multiple, okay, and this can keep on going on for a while, all right, if you wish, and the only thing that's limited to is how big your sample size is, because you need a certain amount of data to support all this this big of a model. All right. So why did we switch things around? Well, we're going to put this into the computer, and and so what we want the computer to do is we want the computer to put together all the slopes together. Okay. And so we don't want the computer output to be like this: y is equal to a slope plus the intercept plus other slopes times x. We want all those slopes times x to be gathered into one spot, and the y-intercept to be isolated by itself. So what did we do? We switched them around. Okay. So now the good thing for this class is that we don't have to deal with all these different multiple factors. All we have to deal with is that we just have one factor, okay, and we can even drop the fact that we have a 1 here and a 1 here, and notice that once we say, okay, we're not dealing with this stuff back here, and we can just drop the subscript 1, notice that this equation now is exactly that equation there. All right. So no matter what computer program that you're using, if it's doing regression analysis, okay, it's going to give you the equation of the line in that form right there. Y is equal to the y-intercept plus the slope times x. So we'll just have to deal with it. All right. But there are reasons for why we do it in statistics like this. Okay, let's move on. Let's say that we went ahead and took a look at StatCrunch. All right. And so, okay, so my screen was cut off a little bit, but that's okay. What you have over here is latitude, right? Here's your latitudes, here's your average area temperature, and I'll show you what you would have to do in StatCrunch to get the analysis here. So we would go to Stat, and we go to Regression. So Stat, Regression, Simple Linear. Simple linear just means that we just have one explanatory variable. So here we would enter our x variable, we would enter the y variable. All right, and after now be careful in entering those, because if you put those in backwards, you're going to have a different line to deal with, and you just did the analysis incorrectly. Everything's going to be wrong at that point with the output. So make sure that you take great care in defining what the explanatory variable is and what the response variable is. Okay, then you would hit compute. So here's the output, and the output that I want to deal with here is this stuff up here. Actually, we're going to deal with this stuff in Chapter 12, and actually this stuff down here we're not going to deal with at all. That's more for your next stats course that talks about regression and goes into it deeper than what we are here in this course. All right. So what I want to focus in on is this stuff up here. Okay. So I've gone ahead and brought it over, and really the stuff that I want to focus in on is these 3 lines right here. All right. So here's the regression equation, right? Here's the sample regression line, and it's in the form of y is equal to the y-intercept, all right, plus what? Plus the slope times x. Times x. Okay, it's always in that form. And so it looks like average area temperature is y. The y-intercept is what? 137. Now, if there was a negative sign out here, you would capture that sign. So that's saying the y-intercept is equal to 137. Now notice there's a plus sign here and a negative sign here. So if the slope is positive, you would just see a positive sign here. but the slope happens to be negative. So the way you really got to think of this is that it still fits in this form. It's just that you can think of it as a plus a negative 2.73 times latitude. Okay, but that's a little redundant in mathematics, and so we just dropped a plus sign. But it does fit this form. Okay, and so what are we going to have to do with the slope then? We're going to have to capture whatever sign is sitting here. Okay, so the slope is not 2.73, it's a negative 2.73. And then obviously our latitude is x. We had a sample size of 10. We had 10 cities that we took a look at. And look at the correlation coefficient for our model. It turned out to be a negative 0.9826. What do you think about that? Well, let's see. So we have certainly we have a negative relationship. Remember, the slope and the correlation coefficient should have the same sign. They do. Notice they're different numbers. Okay, and this is telling us that what? We have a very strong negative relationship. We have a very strong negative relationship. All right, so that's telling us our model's really, really good. Okay, and so since our model is really, really good, we should be able to do some more with this model then. Okay, other than creating that trend line. What can we do with that trend line, and so on and so forth. All right. So that's what we're going to focus in on, is the equation of the line. So the very first thing that we can do, that after we say, okay, we have a very good association between average area temperature and latitude. Okay, and so what we can do is that we can use the sample regression equation, sample regression line, to predict the average area temperature for a city that wasn't in our data. All right, that wasn't in our data, and it's actually very simple to do. Okay, and you'll see why. So what we're going to do is we're going to predict the average area temperature for Nashville. Notice, remember, Nashville wasn't in our data. Okay, so we can use our line, a regression line, to go ahead and make a prediction for Nashville's average January temperature. Okay, and all we're going to need to know is Nashville's latitude. All you're doing here is that you're putting in a specific value for x. Okay, the specific value for latitude. And after you put that value in for latitude, the equation will then make a prediction for a city that sits at that particular latitude, what we're predicting for the average January temperature. That's all we're doing. All right. So what we need is Nashville's latitude. So Nashville's latitude, I looked it up, it's 36. So what are we going to do? We're going to put 36 in for latitude and figure out what average January temperature turns out to be. Now, excuse me, before we do that, okay, whenever you make a prediction in regression analysis, instead of just saying y, what we're going to do is we're going to put a little hat on top of y, and we're showing the rest of the world that we are making a prediction for y using our regression model, using our regression line. All right, so whenever you make a prediction in regression analysis, you're going to put a little hat on top of it. So you're going to see that here in the next line. So notice here we got average area temperature. This is the hat. It got a little distorted here based upon the graphics, but there's a little hat right here. Okay, and notice I put a little subscript here for Nashville. So Nashville's average area temperature prediction, okay, is what? It's 137 minus 2.73, and we put in 36 for its latitude. And so you would put that into your calculator, all right? And what did we get here? I got 38.72 degrees Fahrenheit. So hopefully you would get the same thing. So if you were trying to make a prediction for a city that sits at 40 degrees latitude, you would just go ahead and put in 40 degrees latitude and see what the line is predicting then. All right? By the way, if you actually looked up Nashville's average area temperature, it's 37.5. 37.5. So what do you think? Did our equation do a pretty good job? I think so. That's pretty close of a prediction, all right? And so remember, we had a very strong relationship between x and y based upon the correlation coefficient. And so right here, we shouldn't be all that surprised that our equation did a pretty good job in predicting Nashville's average area temperature. But there are limitations to using the equation to make predictions. First of all, the correlation should be strong, or at least moderately strong. And so, why? Because if you have a weak correlation, do you think it's going to predict very well? Probably not. And so you need something that's at least moderately strong or very strong to start making reasonable predictions for y, given a certain value of x. 2, be aware of outliers, all right? Because those pesky outliers can distort the line, okay? And so it's going to shift the line around, okay? And so any kind of influential outlier is going to shift the line greatly. So you got to be aware of them. And then last one, which I want to concentrate on, is that don't extrapolate. Now I know I haven't talked about extrapolation, so let's talk about this. What is extrapolation? All right, so it's making a prediction for y outside the minimum or maximum values of x. So making a prediction for y, but outside the minimum or maximum values of x. So let's take a look at our line here. So here's our line, okay? Where's our minimum value for x? Well, let's see, Miami, right? Miami set at 26 latitude. And so right here, okay, is 26. And then Duluth, 47, that's our max for x, okay, is sitting right here, all right? And so our regression equation is only good for cities that are between 26 and 47, and that is it. No more than that. The reason why is that we don't know what happens to this line. So this is what extrapolation is that we just simply take this line and extend it out straight. That's extrapolation, okay? And the same holds down here. Extrapolation would just be taking this line and extending it out, okay? But do we know what happens to the line? Do we? No, we don't know what happens to the line. We don't know if this line is going to curve up here, or if it's going to curve down, or if this one's going to curve that way, or this way. We don't know. It could keep on going straight, but we don't know. All right, we don't know. So extrapolation is just taking this line and extending it out straight. But we don't know what happens outside of our data, okay? Actually, let's do this. Let's actually look at data outside of 26 latitude and 47. Okay, so what I did was, in the next slide, what you're going to see is I put in one Canadian city, and then I put in cities in South America, like in Mexico and then South America, and then all the way down to the South Pole. Okay, so let's see what happens when we do that. That's what happens. Okay, that's what happens. So notice here, here's the Canadian city. Okay, then I start putting in cities in South America. And what happens? Does it keep on going straight up? Nope. What does it do? It actually heads back down. So if you think about it, negative 90 degrees latitude is the South Pole. And last time I checked, it was really, really cold there. So you're going to get a very low average January temperature. Okay. What about on the other extreme? So if you go to the North Pole, okay. So if you go to the North Pole, you're going to be at 90. And what happens at the North Pole? It's pretty cold up there too. Okay. And so is the relationship between average January temperature and latitude a perfectly straight line for a lot of latitudes? And the answer is no. Clearly it's not. It is a what? It's parabola. It's parabola. Okay. Now our cities sat between, I believe, here and here. Okay. And so if you just extrapolate, this is what's going to happen. It's going to be this. And it's just going to keep on going up and 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 up. It's going to get ridiculously high. Okay? And so, should we extrapolate outside of our line then? The answer is no. All right? We should not. And so, so be careful, all right? And don't and don't extrapolate the line. All right. All right. So what I want to do is I want to focus in on slope. All right. Slope is a very important thing in statistics with regards to regression analysis. Right. And so we need to focus in on it. So, what is slope? Slope is here's the definition. It's the change in y when x increases by 1 unit. I used to ask people, what do you think the definition of slope is? And I usually get rise over run, okay? Which, to me, that's more of a way of calculating it. Rise meaning the change in y, run meaning the change of x. So, the change of y divided by the change of x. So that's a good way of calculating it. But it's not really the definition for slope. So slope is the change in y when x increases by 1 unit. So let me give you an example, all right? Real simple example. Let's say y is equal to 2 plus 5x, all right? And so I'm going to start with a certain specific value for x. I think it's 2, okay? So notice what I did here. I put 2 back into the equation for x, okay? And so 5 times 2 is 10 plus 2 is 12. So when you put x of 2 in the equation, you get a y is equal to 12. Okay, so let's go back to the definition of slope. It says go ahead and increase it by what? 1 unit. So what are we going to increase x by? We're going to increase x from 2 up to simply 3. Okay, so notice here I've increased x by 1. Okay. And notice what happened to y when we put then 3 into the equation. But 5 times 3 is 15 plus 2 is 17. Okay? So there's y when x is equal to 2. Notice what happened to y. How much did it change by? It changed by a plus 5. Okay? So, and that's what slope tells us, is that when we go ahead and increase x by 1, how much is y going to change? And so without even doing hardly any kind of sophisticated math. I won't even say sophisticated. Without even putting it in the equation, if we put in here 4 for x, and so we increase it by 1, how much should y change by? It should change by 5, right? It should change by 5. And so what are we predicting then for when x is equal to 4 without even putting it in the equation? What are we predicting here? I think if we add simply 5 to 17, we should get 22. All right? There you go. So that's what slope is telling us. How much does y change by when we go ahead and increase x by just 1? Okay? And so, what does that mean with regards to statistics? Well, the slope in statistics then describes the average relationship between x and y. That's why it's so important to focus in on it. This is telling us the average relationship between x and y. And what tells us how strong that relationship? Correlation coefficient. So the average relationship between x and y is described by the slope of our regression line. Okay? And correlation tells us how strong that relationship is. So here's our equation again. And so our slope is a negative 2.73 clearly. Okay? And what I want to do is I want to make an interpretation of slope in terms of the problem. What slope is a rate. Okay, it's a rate, but it can be a funny rate. You know, some rates make perfect sense to us, like miles per gallon or miles per hour. Miles per gallon. How many miles can you drive per gallon of gas? Miles per hour. How many miles can you get in 1 hour at this? Because we're driving at it's speed, right? So if we're driving at 60 miles per hour, we're going to get 60 miles per 1 hour if we keep it constant at that particular speed, at 60 miles per hour, right? So some rates make perfect sense to us, okay? But other rates can be a little funny. Happens if I told you, the slope of some regression equation was dollars per child. And you're going, whoa, dollars per child. What in the world are we talking about? Okay? Well, see, that's what could happen with these rates, okay? And so I didn't tell you that maybe the dollars were healthcare dollars, and how much, and so it's how much healthcare does a family spend per child, all right? And so rates can be a little funny, and so that's why we don't just simply put the slope in terms of a rate, okay? The rate may not make a whole lot of sense to us, but if you put it into an entire sentence, it makes a heck of a lot more sense to us, okay? And so we're going to go ahead and make an interpretation of the slope in terms of line. In terms of the problem, in terms of the problem. So we're going to focus in on that 2.73. What does it mean? Negative 2.73. What does it mean here? All right. And so what I want you to do is I want you to think of is that we're going to start with always increasing x by 1. Start with that. So what is x in the problem? It's latitude. So we're going to increase x latitude by 1. All right. And so what does that mean in terms of the Earth? That means remember, latitude is in terms, think of we have a sphere, okay? Remember you have, like degrees on a circle, but now you have degrees on a sphere, okay? And so when we move 1 degree on the Earth, where are we actually heading, okay? Where are we heading? Are we heading north or are we heading south? We're actually heading north, right? So we're heading further north, okay? Further north, all right? So as latitude increases by 1 on the Earth, right? So we're heading north on the globe. What generally happens? Does it get in North America? Does it get warmer or does it colder in January? It gets colder, right? And so you're going to see that with our interpretation. So the next thing I want you to focus in on is on the sign, okay? So as latitude increases by 1 degree on the Earth, so we're heading north, all right, what happens to average January temperature? Average January temperature will, what? Decrease, because we have a negative sign here. So average January temperature is predicted to decrease, okay, because the negative. So if we had a plus sign here, we would say increase. But we have a negative sign, so we're going to say, oh, it decreases, right? So as latitude increases by 1, as this increases by 1, what happens to average January temperature? It will decrease, okay? It's predicted to decrease by how much? 2.73, what? And then you got to say, okay, well, what was average January temperature in terms of degrees Fahrenheit? Okay? So as latitude increases by 1 degree on the Earth, we're heading north, average January temperature is predicted to decrease. And we're predicting it's going to get colder by close to, 3 degrees Fahrenheit, more specifically 2.73. Okay? So you're going to have to interpret the slope both in homework and the exam. This might be one of the harder things that you got to do in this class for regression analysis. Okay? So you'll get some practice. We're going to do one more example, by the way. All right? Let's do this one. Here's a second example. So when you go out to eat, okay, let's say that you go to a restaurant. It's a sit-down restaurant, okay? So you're at a sit-down restaurant. What is the major thing that you take a look at right away to figure out what your tip's going to be? Now, some people might say, well, did I have really good or bad service, okay? And that might be something that people take a look at right away, okay? But let's think in terms of quantitative variable. What is the very first thing that you could take a look at that will start to determine maybe where your tip's going to be? And I think most people would say, well, it would be the bill itself, right? And so what we're going to do is we're going to use we're going to use the bill as X and to help us predict what the tip is going to be. And so let's say that we went ahead and gathered up some data, and we put the data into the computer, and this is the equation that came from the computer. So we have tip is equal to a negative 0.29 plus 0.16 times the bill. Okay. And both are terms of U.S. dollars. So we have a y-intercept of a negative 0.29, and we have a bill that's 0.16, right? And we have a positive equation, okay? And we have not a positive equation, but a positive slope, okay, to the equation. And that means we have a positive relationship. So that means as bill goes up, what generally happens to the tip? will also go up. All right, we have a positive relationship. Right, so that's it. Let's go ahead and make an interpretation of the slope. So what are we going to do? I'm going to have the whole thing right now at once. So let's do this step by step. What are we going to do to Bill? Bill, we're going to increase by how much? Just simply one what? $1. Okay. So as the bill goes up by $1, what do we predict for tip? So as bill goes up by $1, we're predicting that tip will do what? Increase by $0.16, or another way of saying that is what? 16 cents. So as bill increases by $1, how much tip is going to change by? It's going to increase by 0.16. That's what our prediction is going to be. And that's what I wrote here. So as the bill increases by $1, tip is predicted to increase by what? 16 cents or $0.16. Okay? So hopefully you'll get good at that doing the homework. Okay? All right, let's move on. Let's get away from slope. So slope's really important. Okay? But there's other things to take a look at. Next thing is the y-intercept. What is the y-intercept? What is the definition of the y-intercept? Definition of the y-intercept is the following. It's the value of y when x is 0. So graphically, if you are looking at the line, it's where it crosses the y-axis. Okay? It's where it crosses the y-axis. Because at that value, x is 0. So this is the value of y when x is 0. That's your typical definition in a math course for the y-intercept. Right? Now in statistics, what that means is that since we're putting in a value for for x, and it's a value of 0, all right, what are we doing? We're making a prediction that we're putting in a specific value for x. What are we putting in for x? 0. So we're making a prediction here for y when x is 0. So if you went to our simple equation, y is equal to 2 plus 5x, all we're doing is we're filling in 0 for x. And so if you fill in 0 for x, what do you simply get back? You simply get 2. So every time you fill in 0 for x, what happens? This goes away. And what are you left with? You're just left with y is equal to 2. Okay? So you're always just left with y is equal to the y-intercept. Okay? So when you go ahead and put in 0, basically what we're saying is this is what we would predict for y when x is 0. It's just that right there. That's the y-intercept in a regression analysis type deal, right? So let's take a look at this. So if we put in 0 for latitude, this goes away, okay? And what are we saying? What we're saying is that, now what sits at 0 degrees latitude? The equator, okay? The equator sits at 0 degrees latitude. So what we're saying here is that a city that sits at 0 degrees latitude at the equator has an average varying temperature of 137 degrees Fahrenheit. You see a problem with that? That's awfully hot. Okay, we got to figure out what happened. Okay, we got to figure out what happened here. All right. So let's do it. So I just went ahead and I already said what the interpretation of this is. So when latitude is equal to 0, the city is at the equator. We are predicting the average general temperature to be 137 degrees Fahrenheit. Okay, yikes, right? And so one problem is that, well, do we have any cities in the United States that sits at the equator? The answer is no. So remember, your data is only good for cities in basically North America, okay, and really in the United States. And really, what's it actually limited to? It's actually limited just to cities from, 26 to 47. And what did I tell you just not that long ago? I said don't extrapolate, okay? Don't extrapolate, because we don't know what happens to the line before the minimum and the maximum value. And remember, this is what's going on, is that all we're doing is the y-intercept. What the y-intercept is telling us is that if we took this line straight out, all the way out to what? 0, okay? What's eventually going to happen at when x is 0, okay, y is going to be 137. So this is just going to keep on going up and up and up and up and up. And when eventually x gets to 0, y is going to be equal to 137. And what did I tell you not to do? I told you don't extrapolate the line. So really, the y-intercept in statistics, okay, all you're doing is extrapolating your line, potentially, all the way out to 0. And so, I'm just reminding you here, remember, the curve actually goes back down, okay? And so, don't take this line and just keep on extending it out and out and out and out, okay? So, what went wrong for this particular problem? Well, not really all that much, okay? But there's a warning here, okay? And here's the warning, is that be careful in interpreting the y-intercept, all right? So pay close attention to what I'm saying. I'm saying in order for the interpretation of the y-intercept to be valid, we need to have in our data, okay, values for x around 0. We need data around 0 for x in order to make it a correct interpretation for the y-intercept. Now, why is that? Well, so that means we don't have to extrapolate the line. So if we went back and we actually threw in data around the value of 0 and we extended our analysis past, say, the United States into South America, okay, we could go ahead and make a valid interpretation of the y-intercept in that situation, because we would have values around what? 0, all right? And so we could make an interpretation of the y-intercept as long as we had data around the value of 0 for x, okay? In our situation, we didn't, okay? Which made our interpretation of the y-intercept a little suspect, okay? Actually, a very, very much suspect, okay? We knew it was wrong, but we had to figure out why, okay? And there you go, okay? So be careful interpreting the y-intercept. So truly the most important thing that we should do is be able to interpret the slope. All right. So last thing that I want to talk about are what's called residuals, and these are the errors in our model. Errors in the model. Okay. And so here is a scatter plot, and let's say that the line goes like that. Okay. Let's say the line goes like that. And so notice here that the dots don't all go through the line. Actually, it's very possible that none of your dots will go exactly through the line. All right. And so that means our model is not perfect. It missed here, missed here, missed here, and so on and so forth. And so there's a miss just about at every value with regards to our observations. We missed. Our line didn't go through all the dots, okay? And so what would be the miss? What would be the residual, say, for this dot right here? Well, it would be the difference between here down to the line. That would be what we call a residual. And so there's a residual at every observation in our data set. So if we took a look at this dot, the residual would be the difference between here to the line, here to the line. Not a very large residuals over here, but here to there, here to there, here to there. That's our miss. And notice that means the miss is always in terms of y. So notice from here down to here, that's how much we missed in terms of y. Okay, and so in calculating the residual, it's not that hard. Oh, by the way, anytime that the observation is above the line, you're going to get a positive residual. And anytime it's below the line, it's going to be a negative residual. All right. So you're going to have, in every regression analysis, you're going to have positive and negative residuals. All right. But it's more about how far did they miss. Okay. It doesn't matter if it's negative or positive. It's just how big in magnitude is that number. So the residuals has a simple equation, and all it is y minus y hat. All right. And so really what this says is the following, is that y minus y hat is just simply equal to the actual value for y minus, and what is y hat always? I told you that was a predicted value from the equation, okay? And so if you think about it, so back here, if you went ahead and took a look at, say, this dot right here, right? So we can look at the exact value for y, okay? And then here is the predicted value, okay? And how much is the difference between here to there? Y minus y hat, okay? Because the x didn't miss. The x didn't miss at all, right? X is perfect, okay? It's how much did we miss in y. So like I said, there's a residual for every value in the data. Okay, so let's calculate the residual for Cleveland, all right? In our average ambient temperature and latitude example. So we're going to need the latitude for Cleveland. We're going to also need its average ambient temperature, all right? And so this right here, so if you go back to the data, you're going to see that x is 41, y is 25, okay? This right here, this is the y that we would throw into the equation right here, okay? It's the actual average ambient temperature for Cleveland, okay? Well, where are we going to get this? This is always from the regression line. It's always coming from our equation. So what we're going to have to do is we're going to have to say, okay, well, what were we predicting for a city that sits at 41 degrees latitude? And so what are we going to do? We're going to put 41 in for latitude. And we're going to see, well, what did the average ambient temperature for a city that sits at 41 degrees latitude turn out to be? And so I think if you put that in the equation, I think you get 25.007. All right. So the residual then for Cleveland would be y of 25, and then the predicted value of 25.07. And so we would get a residual of a negative 0.07. And so what is that telling us? That's telling us that our equation did a really good job at predicting the average temperature for Cleveland, okay? Because we had such a small residual here, okay? We had such a small residual. So I got a question for you. Would we want large residuals in magnitude or small residuals? And I think most people would say, I think we would want small residuals. That's telling us that our model is good at making predictions, okay? And so this is another way of looking at how strong our model is, okay? Is that are the residuals small in magnitude or are they large, okay? And so notice here is Cleveland, and actually this is also Lincoln, Nebraska, and notice how close it was to the line, okay? Notice how close it was. So, oh, there we go. I didn't mean to go that far. So do we want the residuals to be small or large in magnitude? We want them to be small. And then y, the smaller the residuals, the better the model is at predicting values for y. The only other thing that I want to tell you about residuals that we should probably have an idea of, I don't know what happened to my pen there, there we go, is that if you go ahead and sum up all the residuals, I just realized that I forgot to put this on the presentation, is that if you sum up all the residuals for any regression model, it always turns out to be 0. So if you think about what that means, then, if you think about it in terms of a graph here, remember you have positive residuals and negative residuals, and if the sum of the residuals always turn out to be 0, what does that mean about the line? The line, that's telling you that this line that we're creating in regression analysis is truly going through the center of all the data, okay? It's truly going through the center of it, okay? That's one really good way of looking at it, okay? So that ends the presentation for this section. Thank you for your time.